Solution concentration is a topic that reappears throughout first semester chemistry and second semester chemistry and is a very important component of any laboratory work in chemistry. We will continue to look at solution chemistry, recapping some of the solution concentrations you are familiar with and introducing to new concentrations that we will use throughout the semester. So here is a typical volumetric flask, and we have filled it with 18 grams of sugar and added water up to the 250 milliliter mark. As you're thinking about solution concentrations, it's really important to remember maybe Shakespeare's famous phrase, "A rose by any other name would smell as sweet." A concentration in any unit always reports the same thing. How much solute you have, the thing you care about, in this case sugar, and how much solution it is distributed in. So we'll start with the solution unit that you're familiar with, molarity, and I hope you have it locked away in your brain that molarity is moles of solute per liter of solution. So in this case, the thing we care about, the sugar, we have 0.1 moles, and this is 250 milliliters of solution, or 0.250 liters of solution. And I do the division that this ratio indicates, 0.1 divided by 0.25, and we find out the molarity is 0.40 molar, and remember that big M is the symbol for molarity. Let's look at the exact same solution but expressing the amount with another familiar unit of concentration, and that is weight percent. And this expresses the amount of solute, in this case sugar, compared to the amount of solution, but all in units of grams, and all multiplied by 100% to get it in terms of a percentage. We have 18 grams of sugar. That's easy, but now the grams of solution is not exactly straightforward. We know we have 250 milliliters of solution, but how much does that weigh? And of course the density can tell us that. So if I take the solution volume and multiply by density, milliliters of solution cancel, and we obtain 255 grams of solution. And so entering that into our expression and doing the division, 18 divided by 255, and then multiplying by 100%, we find out that 7% of our solution is sugar by weight. And so if we poured out 100 grams of this solution, we would know that 7 grams of sugar was also floating around in solution. I'm going to briefly present a unit of concentration that you are familiar with from the gas laws chapter, mole fraction, and that is moles of the thing I care about, sugar in this case, divided by the total moles present in the solution. Well, the moles of sugar, that's we've already used, is 0.1 moles, and the total moles, now that's tricky to get to because I have moles of sugar plus moles of water. And now I need to think about how much water is present. We know the total mass of everything present, that's the solution, but that solution is split into an amount of sugar and an amount of water. And so actually all we have to do is the subtraction of the 18 grams of sugar, and whatever is left over, 237.5, must be the grams of water. We know how much water we have, but mole fraction is asking for a number of moles of water, and so we have to do the unit conversion. How many moles of water are there in 237.5 grams of water? And of course that's just a molar mass. Divide the grams by the molar mass, 18 grams in 1 mole, grams cancel, and we discover we have 13.2 moles of water in this solution. And so now we just add the two pieces together, 13.2 moles of water plus 0.1 moles of sugar, and if I do this division, we find out that a very small fraction of the total moles, 1 would be the total moles, 0.007 is the moles of sugar present. Okay, 2 new concentration units that we will use this semester. One is a slight change to weight percent, and that's called parts per million, and it really is the same setup, grams of solute over grams of solution, but instead of multiplying by 100%, you multiply by 1,000,000. And in general, this is only used for very dilute solutions where multiplying by 1,000,000 doesn't give you a very big number. We can go ahead and plug in the numbers 18 grams of sugar and 255.5 grams of solution, but when I multiply by 1,000,000 I end up with 700,000 parts per million, and that's not typically used. We'll look a little bit more, but it's also the case that parts per million very often is expressed as the milligrams of solute over liters of solution, and this gives very similar numbers to what we see when doing the grams per grams times 1,000,000. Okay, the new solution concentration unit that is going to be important to us is, I can't help this, it's called Molality, and I know that name is similar to Molarity, but they are similar. It's how many moles of the thing I care about, the solute, but now just compared to the kilograms of solvent. And there are a couple of reasons for doing it this way. One is you don't have to have a fairly expensive volumetric flask. All solutions can be made strictly on a balance. You just weigh the grams of solute you need and you weigh the solvent that you're adding. And so in this case, the mass of solvent we've already determined from an earlier subtraction, and the moles of solute remain the same, and so it's 0.1 moles of sugar and 0.2375 kilograms of water is the solvent in this case. And now I'm going to do that division, and you see that we call this the molality, 0.42, and it's a lowercase m. Molarity is an uppercase m. I'm sorry they're so similar, but you'll get used to it. And the numbers are not the same, and this is typical that they are close but vary. And in fact, when solutions are very concentrated, molality and molarity can differ quite a bit. We'll practice with these, first focusing on this new unit of molality.